Okay, so we'll get started. Good evening. So yeah, can you hear me?
Yes, sir. You are clearly audible.
Okay, okay. So we'll start today's session. So I am Diljit Datta. I am a research scholar in Indian Institute of Science. So I will be taking this second session on problem solving in this course hydraulic engineering, which is being taught by Mohammed Saud Afzal. Okay, I'll turn off my video for now because of my network connectivity issues. So okay, so before proceeding with some problems, I will just quickly brush up one or two concepts. So one first thing that I want to see is the variation of pressure in a fluid. So so to see the variation of pressure, first we consider let us consider fluid element, which is being represented in this cuboid. So at a point P, the pressure at that point is P, at this point marked by dot, and the center of the cuboid, the pressure is P, and the weight of the fluid element at that center is W. So let us see how the pressure varies in x, y, and z direction in the fluid. So if we take x direction toward like this, y like this, and z is x cross y, so z will be up. So the pressure the length of the element is taken as delta x, the width is delta y, and the height is delta z. It is mentioned here. So if we take the surface on the left, so what will be the pressure there? The pressure will be like at the center we have P, and the distance from the center to the left end is delta x by 2. So so what is the variation of pressure? It is like we have P at center minus of del P by del x into delta x by 2, because we have moved delta x by 2 and the variation per unit length is del P by del x. So this is the pressure at unit at one point in the surface. So if we multiply by the area, we will get the total pressure on the left surface. Similarly, the pressure at the right surface will be P plus del P by del x into delta x by 2, since there is variation of pressure in the x direction. And similarly, we will be multiplying it by delta y into delta z, so to get a total pressure over the whole surface, this surface. So I will just mark the surfaces for convenience. Okay. So this is for x. So if we and we know that the system is in equilibrium, so we are taking as a static fluid, not a moving fluid. So this whole system will be in equilibrium. So the total pressure on the left hand side should be equal to the total pressure on the right hand side, that is on the x, like equating the forces in the x direction, into delta y into delta z. So if we equate these things, delta by delta z gets cancelled, p and p gets cancelled, so del p by del x equal to 0, since delta x not equal to 0. Similarly, if we take for y direction, again we will get two components, that is on surface A, B, C, D, we will have the force P minus del P by del y into delta x into delta z. This is a total force on the surface A, B, C, D, and this will be the total force on the surface E, F, G, H will be P plus del P by del z. So these two forces will be equal, since the system is in equilibrium in the y direction also. So if we equate this, you will get del P by del Y equals to 0, and this implies okay. Now coming to Z direction, that is a surface ABFE and surface DCGH. So what will be that? And also remember, we have, while taking the forces in a Z direction, we also have to consider the weight W. So this is X direction, this is Y, and now Z direction. So if we take the Z direction of total forces, one is the pressure at ABFE, sorry, it will be pressure, it will be force. And this plus weight W, this will be equated by the opposing pressure in the force on the surface DCGH. So force is known as pressure into area. So what will be force pressure at ABFE? So pressure at ABFE will be P minus, one second, okay. So we are taking Z upwards as positive, so we'll be taking positive pressure upward directions. So force at ABFE will be P plus del P by del Z into delta Z by 2 into del X del Y plus so this W is the specific weight. So if we consider W as the specific weight of the fluid, so specific weight into volume will be the total weight of the fluid element. So volume will be delta X into delta Y into delta Z, and this is being balanced by the force at the bottom surface, and Z is negative in the bottom direction as per our convention. So P minus del P by del Z into delta Z by 2 del X del Y. So if we equate these forces, we'll get del X del Y del Z will be cancelled from all the three terms, and we'll have P del X del Y, P del X del Y will be cancelled from both sides. So after simplification, we will have del P by del Z equals to minus W, where W equals to where W is the specific weight, that is rho G. So delta P equals to rho G delta Z. This is how we get the variation of pressure in the Z direction. Okay, I hope this is clear. Okay, so let's move to solve one question. So in this question, it is mentioned that find the pressure represented by a column of 2 centimeter of mercury. Okay, so to know the pressure represented by a column, so if you take in the column, it is already assumed that it is from on a free surface. So at free surface, the pressure atmospheric is turned taken to be 0 in this case. So if we at a height of suppose 2 centimeter, what will be the pressure P? So we have to use this formula obtained in the previous derivation, that is delta P equal to rho g into delta z. So we know g is like acceleration due to gravity. We know delta z 2 centimeter. We need rho. So rho of mercury will be how much? So rho of mercury is equal to specific gravity. Yeah, that's fine. Mercury into 1000, that is specific weight of water. So 13600. So it is very simple. So we can just, so the delta P equal be rho g into delta z. So delta P is what? P minus 0 equals to, and delta z is given as 2 centimeters, so it will be 2 by 100. So P equals to, if you calculate this, you will get I think 2663. This is very simple. Okay, so this is second question, also based on the pressure formula. So here it is given that depth of 15 meter below depth of find the pressure at depth of 15 meter below the free surface of water in a reservoir. So since the liquid is water, so we know, so P equals to rho g h. For water we know what is the rho. Rho is 1000. G is 9.81 and h is 50. So it will be 147. These are pretty simple questions. Okay. Next up, we will see some pressure measuring instruments. So, what are the two main pressure measuring devices? The main pressure measuring devices are piezometer and manometer. Piezometer is a type of manometer only. It is just that in piezometer we have a open end. So, and by Pascal's law, it says that if we place the piezometer at side or top or bottom, the water will rise to the fluid, water or whatever fluid is there in the pipe, it will rise to the same height, Hm. So the pressure measurement is given as rho g into Hm. Hm is the height of fluid in piezometer. So this is how pressure is measured in the piezometer. So it is measured in with respect to the atmospheric pressure. So this, since the piezometer is open to surface, so the pressure that we measure, that is P, it will be with respect to atmospheric pressure. So this, whatever pressure we measure with respect to atmospheric pressure is known as gauge pressure. The second instrument that is used for measuring pressure is a U-tube manometer. So like, what is the disadvantage of piezometer? The disadvantage is that if we have a fluid whose density is low and we have to measure the pressure in that kind of fluid, then Hm will be very high. So we have to make a very long tube to measure the pressure in case of that kind of fluid. So to avoid such problem, the U-tube manometer is invented. So here we can see the apparatus is given by this, is shown in the figure 2.8. You can see if the pipe is, if any fluid is flowing through a pipe, it will be connected to the U-tube manometer, and the manometer will have a fluid that has specific gravity S2. S2 should be always greater than the specific gravity of the fluid flowing. So manometric, so S2 is the specific gravity of manometric fluid, and S1 is the specific gravity of the fluid in, and generally S2 is this fluid is taken as mercury in the manometer only because mercury has very high density, and it will okay, so there is a question, so 1 second. Piezometer will be always used to measure low pressure only. If there is very high pressure, then it won't be able to, like, we have to construct the piezometer which has the height, this height of the channel, like height of the column will be very high, so it is very inconvenient to make such a piezometer. So that's why piezometer is always used to measure when their pressure is very low, or like slightly moderate also you can use depending on the fluid. Okay, so this is a U2 manometer, and how pressure is measured. Suppose let us consider the figure 2.8a. You can see in this case, suppose P of A1 will be P of A dash, because it is based on Pascal's law, and P of B will be equal to P of B dash. So this is also based on Pascal's law. So we will be equating the pressure. So let's start from the surface, that is PD plus what is the specific gravity of the manometric fluid, S2 into rho into gamma water. Gamma is the specific weight of water, so S2 into gamma water into height y, so that is at C. Now point C and point B will have same pressure because it is at same level and the fluid is same, that is it is a specific gravity of S2. So for C equals to D. Now point B and point B dash will have the same pressure, but the thing is that only difference is the difference in fluid. So at point B we have this C equals to B, so and same pressure, and also B dash also same pressure. So from B dash to A dash will be we are moving down. So again S1 into gamma water into Z, which is equals to P A. So this is how a manometer is used. So you can get PA simply if we take PD approximately equal to 0 because we are taking atmospheric pressure negligible, or you can take PA minus PD, you will get the gauge pressure. So will be PA by gamma W equals to S2 into Y plus S1 into Z. This is the principle of a U2 manometer. Next up, we will see there is a single column manometer. So this is also type of manometer only. The only thing is that U2 manometers are generally require readings at fluid levels at two different points. Suppose if a fluid is flowing through a pipe and we want to see the difference in pressure between the 2 points in a pipe, so in that case you will be using a U2 manometer. But if we don't want to measure at two different points, then we can also use this single column manometer. So what is the principle here? Here the pipe is there, so the pipe and the manometer column will be connected via a reservoir. So this reservoir will help in maintaining this reservoir at cross section is generally taken as 100 times the area of the tube, that is the manometric tube. So and this is usually done to overcome the difficulty in measuring difficulty of measuring point like fluid pressure at only one point. So one thing is that you can use simple piezometer also, but the simple piezometer, the problem is that for large pressures there might be you have to take a very long tube. So in that case, for that case only, we will be considering this single column manometer. So here also it is same only. So initially, suppose the pipe is, so here is a valve, we can, the valve is, I am mentioning with my pen. So if we close the valve, okay, the pipe is not connected to the reservoir. In that case, the reservoir is initially when the reservoir, the only we have filled the mercury, okay. So we have only filled the mercury, there is no fluid, this white fluid, okay, this is, let's take black fluid to be mercury, and this fluid supposed to be water or something, whatever, not water, let's say some, let's take glycerin. Okay, so we haven't filled glycerin in the reservoir yet, so we have only filled mercury through the tube. So it will, the mercury will rise to some level in the tube, in the reservoir. So in that case, the mercury level at this point O and O dash, so the mercury level will be at O and O dash. Now what we do is that we pour glycerin in the reservoir, and we still haven't connected the pipe flow. So in that case, there will be slight, since the glycerin has some weight, it will displace the mercury to some level, and the equilibrium level will be like the the level of glycerin will be moving to C, that is C dash, this is C dash, and the mercury level will be moving to this point B. Okay, now what will happen, now we connect, open the valve and connect the pipe to the reservoir. In that case, so again high pressure will be exerted on the reservoir, and in that case the manometric fluid will be rising to a level D, and this is height is h2. So finally what we have an equation, we will have we can get the equation for we will get the pressure at point A in the fluid by using the manometer equation. How we develop the equation is, suppose let's take from the start, that is PD is almost equal to PA. So okay, PA plus, we have taken the specific gravity of mercury to be S2, suppose S2 into rho W into H2. So H2 is till B. Now from B to O dash, the height is H1. So again S2 into rho W into H1. Okay, and so O dash, so again we will be now moving downwards, plus since we have, when we exerted the pressure from the fluid from the pipe to the reservoir, so as soon as the water or mercury level rise from B to D, so there will be a slight movement like slight displacement of the reservoir level by delta Y. So this is small displacement in reservoir, because the reservoir width is very large and the column width of the tube is very small. So so we have till O dash, and from O to C the height is delta Y. So again S2 into rho W into delta Y. So now we have reached the same level C dash. So from C dash we have to move upwards by a distance of Y and delta Y. So minus of S1 into rho W into Y plus delta Y. So we will get this as pressure at A. Oh sorry, we take P atmosphere. I hope it is clear till now. Any questions till now? Okay, I will move on then. So let's put on the values. So let's say P ATM to be 0 plus H1 plus H2 plus delta Y into S2 minus of delta Y into S1 minus of Y into S1 equals to PA by sorry, this is not rho W, okay, this is gamma W, that is specific rate, PA by gamma W. So PA by gamma W will be given as 2 into and okay, and see how this is comes. So we also have one equation. One is that, so when we displace the column in the reservoir by delta Y due to exerted force from the fluid flowing in the pipe, so again at the same time there is a rise in height of mercury by a volume by a height of H2. So A by conservation of mass, A into H2 equals to A into delta Y. So area of small a is the cross section area of the column, and A cross section area of reservoir. And if we put this for values in the above equation, we will get this final equation. Now we can construct a very sensitive manometer, sensitive single column manometer, by taking the manometric channel, that is tube, to be inclined. If we incline if we incline the manometer tube, in that case we can measure even very small change in pressure also. It is very sensitive. So what is the equation? Everything will be same. Everything will be same as before. Only thing is that in case of H1, you will have H1 by H1 sin theta. So if this is H1, this is H1 sin theta. So the height will be H1 sin theta. Okay. So when you take H in this equation, replace all H1 and H2 by H1 and H2 by H1 sin theta and H2 sin theta. Rest everything will be same. The only advantage is that because it is inclined, small for even, it's not gravity, it's due to the angle. So let us see. So let's write the equation. I will show you. So PATM plus S2 gamma W into H2 sin theta plus H1 sin theta rest. So PATM is taken as 0. So what will have PA by gamma W as 2 and after final equation we will obtain as H2 into S2 if we replace that again small a by capital. So this small a by capital A will come from the conservation of mass. Here also the conservation of mass formula, that will be, one second, I will just shift. Will be coming as A into delta y equals to small a into H2. This won't be H2 sin theta, because the volume, you can see, if to change in delta y in the reservoir, there will be change of H2 only in the pipe. So you take the net change in volume, not H2 sin theta. So if we take this equation and okay, and so if A by A is negligible, suppose if we take capital A is much greater than A small a, so that is generally we take reservoir with cross section area to be 100 times generally tube manometer cross section area of the manometer tube. In that case this value will be negligible. So PA by gamma W equal to H2 into S2 into sin theta. If theta is high, if suppose theta is not like in this case we are taking theta from the vertical, so theta should be around, like suppose we take less than 90 degree. In that case, even for small height also we will have a value that is showing high value. So this is from not from the gravity, this is from how the manometer equation is derived. Okay, so here is a question, this is like from past year only. So in inclined column manometer is used for measurement of small pressures, because it is highly sensitive to even small values. So what's of the following, next come to question number 4, what is the following is the limitation of manometer. So the thing is, the manometers are fragile because generally it is made of glass. Since we have to see the level of mercury up and down, we will be making it generally glass, so it is fragile. And also generally if we take piezometer in case of YouTube manometer or this one, even if we construct this like single column manometer, we will have to make a reservoir again, then connect to a pipe. So in that case also, we have with making these things in glass, it becomes a bit bulky also. So this is also, and also if we take piezometer, then we will for like if a fluid has a very less specific gravity, in that case the manometer piezometer height will be very high and you have to take so much of amount of glass to construct it. So in that case it will be very large and bulky also. And thirdly, capillary effect. So capillary effect can also be important thing in manometer. Suppose if we generate from experiments, it has been found that if the manometer with diameter is less than 12 millimeter, then the capillary action takes place. I taught capillary action in the last class. So the manometer fluid, that is whatever mercury or whatever, it will be rising in the and the surface tension will not be negligible, and this will cause capillary rise in the manometer column. So this can again give this will again give erroneous results, yeah, meniscus. So all the above, so all the three problems are relevant to manometers. So the correct answer for this question will be all of the above. Okay, now we'll solve a numerical. So it is, so calculate the pressure at a point 5 meter below the free water surface in a liquid. Pressure at a 5 meter below the free water surface in the liquid that has a variable density given by that. So density is variable. We have given it varies with height. So what we found? We found that in the equation that I derived in height, delta P equal to rho G delta Z. Okay, since if in case of Z we are taking Y, since Y is taken as vertical direction here, okay, we'll take Y for ease of convention, rho G into delta Y. And since rho is varying with Y, we cannot simply directly calculate like rho G into Y, so we have to integrate the value. So dP, so we have to pressure at a point 5 meter below water surface, so 0 to 5 integration of 0 to 5 rho G dy, and so it will be 0 to 5 350 plus I think A is 8 y, you can bring G out and dy. Delta P equal to 9.81 into 350 into 5 plus 8 into 5 square over 2. So if you put the units, you will get around I think 18.15 kilonewton per meter square. It's very simple. Just you have to mind that since density is variable, you cannot directly calculate by rho Z. It's that formula. You have to integrate the value. So this is again one question. This says, okay, we will be solving this question now. Okay. So two pipes are shown in this figure. One is A and one is B. Now I think A, yeah, conveyor toluene, one has toluene and other pipe carries water. So the toluene has I think specific gravity of 0.875 and the other is water, so specific gravity will be 1 only. Both the liquids in the pipes are under pressure. The pipes are connected to a U-tube manometer as shown, and the hoses connecting the pipes to the tubes are filled with corresponding liquids. Find the difference in pressure in the two pipes if the level of manometric liquid having a specific gravity. One second. Okay, so the manometric liquid has a specific gravity of 1.25. So as manometer equal to 1.25 is 2.25 higher in the, so we have to generally find PA minus PB. So we'll just simply write the manometer equation. What? So it will be PA. So no, B to E is not manometric fluid. I think it is from D to E is manometer. This is manometric fluid. I am marking it. This is the manometric fluid till from B to E. It is the fluid that is water, and from A to D it is toluene. So we will simply write the manometer equation. So P at A and P at C will be same. So we can say PA equal to PC also. So so from here to D, the height is 1.5. So SA equal, I'll just write the equation fully. SA into gamma water into how much? Into 1.5, right? So now from D and D dash will have same value of pressure because it is same fluid and the height is same, and from D dash to E the height is 2.25. So and since it is moving up, so pressure will be decreasing from D to E. So minus of S of manometer into gamma W into 2.25, and now from E to E and F will have same pressure value because it is the same fluid, and F to B the height is again 2.25 plus SB will be what, 1 into gamma water into 2.25 equals to PB. So we have to find PA minus PB, so that's all. So we take PB minus PA, we take gamma water down, it will be SA will be 0.875 into 1.5 minus 1.25 into 2.25 plus 1 into 2.25. So if we calculate the value, we will get I think around 7.35 I think. So this is just simply applying manometer principle to two pipes where two different fluids are flowing in the pipes. Okay, so we're done with manometers. So now we'll be moving to types of flow and then covering some part of fluid kinematics. So there are mainly 5 flow types. One more flow type I have okay, let's mention here. Laminar and turbulent. So one first type of flow, two types of flow that we consider as steady and unsteady. What is a steady flow? Steady flow is when the parameters of fluid flow, that is acceleration, position, then velocity, these parameters del by del t equals to 0 if they don't vary with time. If they vary with time, then it is called unsteady. Secondly, if these parameters will take all the three directions, so if they vary with position, then if they don't vary with position, it is called uniform, else it is non-uniform. And 1D, 2D, 3D, you can see 1D is like if you just simply just I will be mentioning, if we have this, one second. One D is like it's flow in one dimension, so in that case the velocity profile will be like this. So fluid is flowing in this direction, velocity profile will be only varying in x direction, it won't be varying in y. So if it is two-dimensional flow, let's consider like this. In that case, the velocity profile will be varying both along x as well as y. So this is 2D flow, and if we take a 3D flow, in that case velocity will be varying in, I can't show 3D properly, it will be varying in both x, y and z. And next up we have rotation, irrotational. Rotational flow is when there is angular deformation, that is rotation component is given by half of, suppose del v by del x minus del u by del y. This is I think given as slab rotation component. So this is for rotation in z. Similarly, we can get wx, wy. If these values are not 0, then it is called as rotation flow. That is there is also angular movement in the flow. And if these values, all the rotation components are 0, then it is a irrotational flow. And lastly, we have laminar and turbulent. Laminar flow is when fluid flow is in layers. So there are like fluid flow in different layers, layer by layer, then it is called the laminar flow. Else, if the fluid flow is haphazard, then we get turbulent flow. And in this turbulent flow, it is always unsteady, it cannot be uniform. So turbulent flow is always unsteady, uniform, and turbulent flow, there will be eddies formation. So these will be taught in the subsequent lectures. So these are types of flow. And irrotational flow, one main point you have to remember that ideal fluids will always be irrotational. This is one thing. And the second thing is like real fluids with negligible viscosity. So viscosity is the prime factor that gives rise to shear in a flow. If there is a shear, then the different layers of the fluid will be moving at will be interacting with each other, and different and this may give rise to a change in moment, change in angular momentum. So in that case, so this will give rise to rotational flow if the viscosity is very high in a fluid. So if the fluid flow is negligible viscosity, then we can say that the real fluid can also maintain irrotational flow at times. So next up I'll be covering some problems from fluid kinematics. So this is a basic question. So local acceleration in a fluid flow situation exists only when. So let's say acceleration is a function of, let's take three components will be there, ax, ay, and az. If we take only ax, so acceleration is, it's like x by del t plus del plus del okay. Now comes, this is one part that comes due to local part, it's only due to, that is only due to change in time. So now if the parameter u can also change in u, v, or even the w can also change in space. So we are taking x direction, so u, v, and w, all the three components of velocity can vary in x direction. So due to change of these velocity components in the x direction, this is also give rise to a acceleration component. So how will we consider that component? So first will be del u by del x into del x by del t plus del v by del y. Now 1 second. Just a second. Okay, let's start the derivation again. I got this is not a proper way of starting a derivation. Okay, so ax is given as du by dt, and du by dt is like rate of change of u with respect to in, and this is not v and w. So u component can only change in x, y and z direction, and this is only cause this is only give rise to acceleration in x. So if you take du by dt, so it will be first you can change with respect to time, u with respect, also obvious x, y, z and t. So you will change with respect to time, you can change with respect to x here, you can change with respect to y, and y can also change with respect to time. Okay, this is just chain rule. And also you can change with respect to z into z with respect to time. Simple chain rules. So it will u into del u by del x, it will be v, del y by del t is v into del u by del y plus w into del u by del z. So this is acceleration, and this part is convective acceleration. So when local acceleration is 0, means what, del u by del t is 0. So this will happen only when the flow is steady. And du by dt is total acceleration in x direction. Similarly, ay will be dv by dt, az will be equal to dw by dt. Okay. Okay, next. So these are covering three basic concepts. One is streamline, the second is path line, and third is streak line. Streamline is what? Streamline is it's an image. It's not that we are drawing a streamline like that. It's an imaginary line, like in the imaginary curve in the fluid flow. It is drawn in such a way that is tangent to the streamline will also always give the velocity in the direction of the flow. Okay, just write the definition for clarity. gives the velocity direction at that point. So if this is a streamline, so this is tangent, so this will give velocity direction of these vectors. So tangent to a streamline will give the velocity direction. Now second is path line. So it is like following one particular fluid particle. So if we take one particular fluid particle, so how the fluid particle has moved over time, and then tracing that path of that particle will give the path line. Tracing path of fluid particle at okay. So how is velocity direction different from path of the progression? So no, the thing is that when we are taking the velocity direction, we are taking the fluid as a whole. Suppose it is flowing through this kind of pipe, suppose, so the streamlines will be like this. So it is like how the fluid is flowing, it's not considering only one particle. Okay, so this whole fluid will be having different streamlines, and each streamline corresponds to the velocity at that point and velocity direction at that streamline along the fluid flow. When you are taking path line, it is like tracing only one particle. Suppose we have one particle, it can at different instance of time it can flow different, it can have different positions. So then tracing this path will be the path line. Yeah, in case of steady flow, so when the flow is steady, streamline and path line will be same. In that case, the path of progression and the velocity direction will be same. But if the flow is unsteady, in that case there will be a change of position with respect to time. So what unsteady flow, position change with respect to time. So when the position is changing with respect to time, so this particle might have one position at here, at next instant it might be here, but the fluid flow might be in this direction, but the particle might be changing its position with respect to time. So in that case, the path traced by one particle will not correspond to the streamline. So in case of unsteady flow, but when you are taking steady flow, in that case, at different instance of time only, the particle will be tracing the same path as the streamline, and both path line and streamline will be same. I hope this is clear. And lastly, there is a streak line. So what is a streak line? Streak line is the locus of points of all fluid particles that has passed through same point. So here is a diagram. So this is showing the streamline streak lines and the path lines. So 1 2 3 like this represents the time. So it starts from 0 1 2 till 10 seconds, and whatever is mentioned is, suppose we have taken the first particle. So first particle will be coming out from here at 0th second. So we are mentioning the position of the particle at first particle at next second, subsequent time here, that is at 1 second. So after that 1 second it will be here, at 2 second it will be here, 3 second, 4 second, 5 second, 6 second, like that. So it will be following this, this first particle is following this path line. Now secondly, the second particle will be coming out at time first second from this from this dye injection point, and at the second it will be here, at third it will be here, fourth, fifth, sixth till 10 second will be following this pathway. Similarly, all the 10 particles will be will be living at each second, that is from 1 to 10 it will be following different path lines. So its dotted lines represent path lines. And now what is a streak line? Suppose we take a particular instant. At a particular instant, suppose at we consider 3 seconds. When we consider 3 seconds, so the first particle has already moved till here at third second, the second particle has moved till here at third second, and the third particle has just come out and it is here at third second. So at third second all these three particles has come out from the same point, that is, they are in the past they have come out from the dye injection point. So at the particular second, at the third second, this is the locus of the particle, this is the streak line at t equal to 3 seconds. Similarly, we can get the locus for t equal to 6, 7, 4, 5, whatever time instant we want, we can get the locus at different time instants. So this is how streak lines and path lines are obtained. Okay, so there are two conceptual questions based on the streamlines and path lines. So first is very easy, I think. So in a steady flow, streamline, streak line, path line, everything will be identical, since rate of change of position of the particle will be 0 in for all the three x, y and z directions. So the correct answer is option D. Second thing is, streamline is a line which is normal to velocity of the vector, no. Which represents the lines of constant velocity potential, no. Which is normal to lines of constant stream function, no. And which is tangential to the velocity vector everywhere at a given instant. So it is option D. Okay, so we'll solve one or two few questions based on streamline. And yeah, so how to get the equation of streamline? So equation of streamline passing to the origin in a flow field, u equal to cos alpha, v equal to sin alpha for a given constant alpha is determined as. So we have, suppose we have taken this streamline that is passing to origin. So this is the velocity vector capital V, small v is the velocity vector in y, and u is the velocity vector in x. So the equation of streamline will be obtained as dx by u equal to dw by z. We are not considering dw since it is 2D flow. So we have dx by cos alpha equal to dy by sin alpha. So dy by dx, so if we integrate x sin alpha equal to y cos alpha plus c, c is the constant of integration. So now it is it is mentioned that the streamline passes through the origin. So if the streamline is passing through the origin, so at x equal to 0, y equal to 0. So in that case, c equals to 0 at by using the condition. So what is the equation of streamline is y equals to x sin alpha by cos alpha equal to x tan alpha. Okay, so the next question we have, one second, yeah. So we have given flow field phi is given as 2xy minus x. So determine the value of velocity v at point 2, 1. So when we have the flow field, so we can get u as del phi by del x, and also phi is also called the potential function. I think you have been taught in class, and v equals to del phi by del y. So just differentiate partially. If you partially differentiate, we will get u equals to 2y minus 1, v equals to 2x. So now point 2, 1, what will you get? Okay, we can just put the value u equals to 1, v equals to 4. So capital V equal to under root and then there will be a just the brush up of continuity equation. So I won't be deriving the continuity equation because it has been already been derived. So I will just say the like a generalized form of the continuity equation is this. That is del rho by del t plus del rho u by del x plus del rho v by del y plus del rho w by rho z equals to 0. So now in case of steady flow, del rho by del t equals to 0. So the equation becomes now second condition is steady and incompressible. If we take incompressible, means rho is equal to constant. So in that case we can take rho out of the derivative, so the whole equation will become del u by del x and also we can also write the continuity equation in the derivative form. So we can write that in, and that is in the vector form, sorry. So just break del rho u will be rho just plus rho del w by del z equals to 0. We have just expanded all the terms, and these 4 terms we can club to get d rho by dt. This is called as material derivative of any property, and we can see rho of and del u by del x. Del u by del x can also be told as grad of u, that is rate of change of u with respect to position. So u, v and w are 3 vectors from velocity vector 3. So it will become as where v vector equals to u I cap plus v j cap plus w k cap. And lastly, the most common form of continuity equation that we use in, that can be used as conservation of mass also in 2D equation, that is a v equals to constant, and this is only when they are, that is rho is equal to constant, that is incompressible. If compressible fluid, then you have to consider rho a1 v1 equals to rho 2 a2 v2. I hope this is clear, and this is basics only. Okay, so I'll solve one question here. In a steady flow of a compressible fluid through a pipe, the density, area and velocity of a particular section are given 1.5, 0.5 and 3, and our section has density this, and what is the velocity of the at that section. So it is that simply this above formula we have to use rho 1. I think it is okay. So you can simply solve this formula. Okay, if it is given in assignment, it's fine. Okay, so this is all about continuity equation, and now we come to velocity, potential and stream function. So velocity potential is given as phi, so u equals to del phi by del x, v equals to del phi by del y, phi by del z. Now for steady you can also write minus, it's whatever convention, if you follow it, it's based on that. You can either flow plus convention or minus convention based on it. So if we take a steady incompressible flow, in that case the continuity equation is del u by del x plus so you can just substitute here the value of u, v and w, and it will get so, and this is called the Laplace equation. And also one more thing, this velocity potential exists only for irrotational flow. This derivation also I think has been done in class, so I won't be going to a derivation of that. And secondly, stream function. So stream function exists only for 2D flow, it doesn't exist for 3D flow. So here it is given as u equals to minus of del by del y, and v is given as del psi by del x. So you for a irrotational, and this exists for both rotational and irrotational. And we can get a relation between phi and psi also. So again, if we substitute phi like u and v in the continuity equation, you will again get a Laplace equation for in terms of psi also for irrotational, steady and incompressible flow. Next, so it is I think it's a very basic question again. So velocity, potential, psi, phi satisfied Laplace equation is represents the possible flow. It is steady, incompressible, and irrotational. Okay, so I will solve one question on streamline. So a stream function is given as phi equals to 2xy, so that the flow is irrotational, and determine the corresponding velocity, potential, phi. So how will you proceed? So since the flow is given as irrotational, so we can assume that the psi also psi also satisfies the Laplace equation, also called Cauchy-Riemann equation, you can say. Okay, we'll just proceed like that. So irrotational fluid is given del square phi psi by del x square plus. So if we substitute the value of psi in this equation, what will you get? Okay, so to get the value of psi, so let's del psi by del x equals to 2y, and del square psi by del x square equals to 0. And del psi by del y equal to 2x del square psi by. So we have seen that del square x by del psi x square is 0, and del square psi by del y square is 0. So if we substitute here, if we substitute here 0 plus 0 into 0, so the flow is irrotational. Now to find phi, it is simple. So del phi by del x, it will be equal to del psi by del y. This is based on for u. So what will you get? Del phi by del x equal to 2x. So phi equals to 2 into x square by 2 plus c. Okay. Since only one variable is present, we can directly integrate 2x into delta x plus c. So it is x square plus, no, it won't be c, it will be a function of y, since we are taking partial derivative. Again, by considering v, del phi by del y equals to minus of del psi by del x minus 2y. So del minus 2y delta y. So if we integrate, phi equals to minus y square plus function of x. So therefore phi equals to x square minus y square. So again a very simple question. So u is given as y cube by 3 plus 2x minus x square y, and v is given as xy square plus minus 2y minus x cube. So obtain psi. So if we take u is equal to minus of del psi by del y equals to x square y. So we'll integrate and we'll get psi equals to minus of plus 2xy minus of function of x. This is one. And secondly, if we take p, so del psi by del x equals to minus of x cube by 3. So again you will get integration of del psi y square x square by 2 will get, because y square is not dependent on y, again 2y into x and minus of x cube. So minus of x to the power 4 by 12 plus function of y. Now from 1 and 2 we will get, we have seen so yeah, there is one mistake here. This will be minus and this will be plus, since it is multiplied by minus in front. sorry. So yeah, so x square y square by 2 are common, minus 2xy is common, so the only two in minus x4 by 12 and minus y4 by 12, so these two terms will be combined, so net phi will be x square y square by 2 minus of 2xy similarly we can obtain phi also. So for phi minus of del phi by del x equals to y cube by 3 plus 2x minus so again if we integrate, so minus delta phi y cube x by 3, so 2 into x squared by 2 and minus of y x cubed by 3 plus function of y, again minus of del phi by del y equals to from the v equation we have to obtain that xy square minus 2y minus x cubed by 3. So minus we will get minus phi equals to x into y cube by 3 minus 2 into y square by 2 minus x cube y by 3 plus function of x. So from both terms we can see what are the common terms. I think x y cube by 3 is common and minus x cube y by 3, so x square plus y square will come, therefore minus phi equals to square plus x taking the common term, so phi equals to and thirdly we have to prove that it is irrotational, so you have phi, you have del phi by del y, so just find del square phi by del y square, or you can take from psi also. We have psi, del psi by del x we have, so let's find del square psi by del x square. What will be that? So we have del psi by, so it will differentiate again, y square minus 2 y square minus what, x square, right? Y square minus x square, and del square psi by del y square, so we have del psi by del y equals to minus of this, so if we take del again one integration, one differentiation, so it will be y square minus x square. Second term will vanish. Okay, so it will be minus equal to, if we add these two, we'll get 0. Okay, so if you have any doubt, you can ask, because we are almost in the end of session. So okay, anything else? In class, till what part you have been covered till now? Is it a laminar flow and turbulent flow, or like it is still in fluid dynamics, that differ like momentum equation and these things? What is being taught, like what is going on now? Okay, laminar and turbulent flow is completed. Okay, we'll cover all those things in next class only. Today it will be too early to cover all those. If you have any numerical doubts or any conceptual doubt, you can ask in chat only if you want. That I have not taught also, like maybe you can general doubt if you have from week 2. I will try to answer if you have any doubt. Okay then, because this part is very simple only, I think, not very like too difficult problems and all here. The simple part only, after later turbulent and laminar flow, there only like difficult problems will come. So you are doing BTech or? Okay, so you have passed out BTech. Okay, so then you have learned this fluid mechanics, I think, during your BTech. That's good. Okay, then if you don't have any, okay. This is basic FM only. Later only, I think we'll come to like core hydraulics, that the hydraulic gauge line and these kind of things will come. So this is basics. So we'll see. Okay, then if you don't have any doubts, you can leave the meeting. Thanks for attending. psi equals to constant. So we are in the end of final parts of this session. So I'll be just explaining some equipotential lines. So we have two variables. One is phi equals to constant and psi equals to constant intersecting each other. Now slope of this curve, slope equals to del y by del x, which is equal to del phi by del x. IV. No. Now at point of intersection, what will you get? You will get minus 1. This implies the perpendicular to each other. That is and this forms a flow net. So that's all for today. I will be winding up the session. Thanks for attending, everyone.